Hello everyone. In this lecture we're going to look at the prediction portion of the course. So our topic is linear regression and correlation. Now before we actually talk about the idea of regression and correlation, let's just very briefly review a little something from your algebra. I know it's been a while for some of you since you have done this. But if you recall from the algebra classes, in an algebra class, the equation of a line is given in several forms. This is called the slope-intercept form of a line. That may seem familiar to some of you. If not, that's okay, but that's what that is. So the form is y equals mx plus b. Here y and x are the variables, m and b are numbers. Now m is called or known as the slope of the line, and b is the y-intercept. It's actually the y component of the y-intercept. The variable x is known as independent variable, and variable y, we call it the dependent variable. And we're going to pretty much stay with those throughout the regression topic as well. Now, the slope of a line, if you remember the interpretation of the slope of a line, is that it is what they call the generic definition is rise over run. But then exactly what is rise over run? Well, the rise over run, more specifically or technically speaking, is the change in y over change in x. That means as you go from one point to another point on the line. Okay, so for example, on this line, if I go, let's say from left to right. Okay, so let me actually draw something here. So I'm going to look at, let's take a look at this line actually, the one in the middle. Okay, so in this line, there you go. Let's say I go from this point to this point on the line. Okay, now the change in y is that much, while the change in x is that much. So the ratio of those two numbers, the vertical change y first divided by the denominator is a change in x, gives you the slope of a line. And remember, the slope of a line gives you the orientation of that line. So that's pretty much what that's going to be for us. It gives you, again, the orientation or the slant of the line, if you will. A line that has a slope 0 is a flat line. That's the one on the left. B sub 1 equals 0. That means the slope is 0, horizontal line. For a horizontal line, there is a change in x as you go from one point to another point, but there is no change in y. So the numerator of this fraction is 0, which gives you b1 is 0. If the line has positive slope, this will be the orientation of the line. And for negative slope, this is the orientation of the line. Okay, so that's the significance of the slope of a line. Now, in statistics, the equation takes on a slightly different form, and there's actually a good reason for that. As we get into multiple regression, this kind of a convention works out very nicely. Okay, because in a multiple regression we have many independent variables. So the idea of b0, b1 goes to b0, b1, b2, b3, b4, and so on. So it's a much better way of doing business. And therefore, we're going to follow that convention. The equation in statistics of a line is going to be b sub 0 plus b1x, where b sub 0 here is going to be the y-intercept and b1 is the slope, the number that multiplies by x. Okay, so here's the objective of what we want to do in this lecture. We would like to be able to predict the value of one variable, which we call the dependent variable, from the knowledge of another, which we call the independent variable. Okay, so that is what we want to do. And the data in this case is going to be what we call bivariate data. That means you have an x and a y component, just like an ordered pair x comma y is. the x, y could be either qualitative or quantitative. In fact, we do have ways of handling both cases, but for most parts, in simple linear regression, first order model is what we're going to be looking at. For us, both of these are going to be quantitative variables. Okay, so our focus is on both variables being quantitative in this lecture. Now, in our regression model, we're going to make an assumption here that the values of x is going to be fixed. That means they're not random and they're measured without error, while the y values are random and there could be error in the measurement of those. Okay, so that's an important assumption for us. Now, the independent variable, these are some of the names, other names that independent variables are known by. They're also called explanatory variables, predictor, or a regressor, while dependent variable is known as response, predicted, and regressed. So I guess for those who call x a regressor, so same folks call y regressed. If you call x predictor, then y would be predicted, and these kind of go together. Okay. Now, the term regression, actually, this is an image of Sir Francis Galton, who actually, again, pioneered this work. He was a polymath. That means he was a jack of all trades. So he was not just in one field. As you can see, he was in a lot of different various fields. Early 1900 is when he actually discovered the idea of regression, and he was interested in doing the work that he did. If I recall correctly, in his work, he was actually interested in looking at the heights, the relationship between the heights of fathers and sons and their sons. And the premise being taller fathers will tend to have taller sons. So it is in that study where he came with the term regression, which means to go back. Now, why did he pick the term regression is because in that research that he was doing, he noticed that beyond a certain height, the height of the sun regressed toward the mean of the sample. So, or it went back towards the mean, and that's where he came up with the idea of regression. He called it regression to mediocrity. So anyway, this is a gentleman who's come up with the idea. And the idea is pretty actually simple. Suppose we have bivariate data x, y as I have it here, and we would like to be able to fit a line through this data points. Okay, so for example, let's say I could draw a line like that. That doesn't look too impressive, does it? Because we're going to use it to make predictions. So for example, for this level of x, my predicted value is going to be that. And then notice that's not a good prediction. At this level of x, let's say at this level of x, my prediction is going to be that. So this does not seem to be a good prediction model. Okay, so let me remove the orange lines here. So let's actually draw another prediction line in here. Let's say, how about this one? Is that any good? Probably not. Doesn't even go through any data points. So you get the idea. We can draw these regression lines. Well, not a regression line, but we can draw these lines so many different ways. That one is better than the other two I did. At least it's going through some data points through here, right? So that's another way. Which begs the question, how are we going to determine, or how are we going to decide what's the best line of fit? So for example, let's say that one now looks better, right? Because it's kind of going through the middle of that cluster, and I think this is the best line of fit that I can draw through these data points. Okay, but that's the idea of regression line. So the graph that you're looking at is called a scatter plot. A scatter plot is a two-dimensional plot of x versus y. Okay, and that's what that is. Now, We're going to look at in a moment the criterion that we're going to select in order to call the best line of fit the best. Okay, so here's the idea behind the line of best fit. Okay, so this is in fact the criterion we're going to look at. Is the one that gets as close as possible. This is of course a non-technical criterion. This is more of a hunch and more of a common sense model for the regression. We would like to have a line that gets as close as possible to every point in the scatter diagram. Now, one thing we could do, for example, we could not do, for instance, is this. We cannot draw zigzag lines like this. We cannot do that going through the data points. We want just a single line, with just one line that can do this. So we don't want multiple lines. Okay. Therefore, now put our intuition into mathematical expression. That's what this part is. Mathematically, the line of best fit, therefore, is a line that's going to minimize the vertical distances from fitted line to that of the observed y values. And that line is called the regression line. Okay. Now, to clarify what that line just read. So here you're looking at the actual y value. And this is, let's say, so I'm looking at just a single observation here. Okay, so I singled out one observation from among many observations. And this is, let's say, hypothetically, the line of best fit. So if this is the line of best fit, that means the point that's on the line is the predicted value at this level of x sub I for some ith observation. Okay, and keep in mind that this is where x is. Okay, now, if you look at the difference here, this is where the actual value was observed, and this is what the prediction line predicts it to be. Clearly, they're not the same. So, there is a difference between the actual and predicted value. Well, that difference between the actual and predicted value, which is the error of our approximation, is called the error or residual. In fact, that's what that is. So this is the ith residual. E sub I is the ith observation, and that's given by the actual value minus the predicted value. And you can see that. Now the residuals could be positive or negative. In this case, y sits above the predicted value, which is y hat I. The caret sign means predicted value. Because this is a higher point than this, so the difference is going to be positive. So if you have a positive residual, that means we are underestimating the actual value. If you have a negative residual, it means we are overshooting or overestimating the actual value. And that's going to happen in a regression analysis. Sometimes we overestimate, others we underestimate. So these residuals could be positive or negative. Okay. So hopefully I was able to explain what the mathematical premise of what we're about to do is about. Now, what we just described is formally known as least squares criterion. Sorry, this should be not list, but rather least, meaning the smallest or lowest. Okay, so it is the least squares criterion that we're going to follow. And again, the line that best fits the points having the smallest possible sum of squared errors means these errors, the best line of fit is the one that has a minimum of that for every data point. Now the reason we have indeed here we say squared errors, the reason it's squared is it turns out that actually if I do some of these residuals, and you can prove this mathematically. Let me maybe write that. Well, I think I have that coming up in a few moments, so let me hold off on this. Yes, I do. And it is right in here, in fact. It's right in here. It turns out that the sum of the residuals is always going to be 0 for the regression line. So in order to get around that deficiency, what the statistician have done is they said, well, why don't we square these deviations so that way when we add them up, we're going to be adding a bunch of positive numbers, right? Because the square of positive or negative residual is always positive. So it's for that reason that we're looking at squared errors. Okay, so just want to clarify it. So that's going to be our criterion. And here I actually have these residuals for 1, 2, 3, 4, 5, 6, right? So 1, 2, 3, 4, 5, 6 observations. So notice again, this residual is positive, negative, positive, negative, positive, negative. If we add all of these numbers mathematically, the expressions, they will end up being 0. Okay. So that's good. We actually laid out the foundation for the line of best fit. Now, let's take a look at this one. So what we're actually going to look at in this lecture, in our course for now, we're going to actually consider what we call a simple linear or first order regression model. It's called simple because there's only one independent variable right in here, 1x. Okay. And it's a first order because, again, x is to the first power. Okay. Now, the population regression model, that means if you have all the possible bivariate data in the population, millions, millions, and billions of those, and you fit a line through those multitude of points, this is going to be the equation of that line, which we don't know. Remember, population parameters are unknown, so we don't know these numbers. Therefore, what we have here, this is the population regression model, right? Let me highlight it in green. And this model is actually going to be unknown, right? The betas, if you will be unknown for this model. Okay. And they need to be estimated. Now, the sample equivalent to what we just wrote up here, this is the sample equivalent to it. Instead of y, we have y with a hat, means predicted values of y. And beta 0 becomes b sub 0. Beta 1 becomes b sub 1 in the sample. Okay. And of course, b sub 0 is the y-intercept, b1 is the slope. And y hat is the predicted value of dependent variable. Okay. Now, just a note here as far as like what is it that we are predicting, and at the very end of this video, which is going to be probably another hour and a half, you're going to see what I've tried to do is try to draw some kind of a three-dimensional sort of graph for you that will explain this. And then I'll be able to clarify what this expression, this line is reading. So you gotta hold off until then. Or you can fast forward the video to the end and you'll see what that means. So, but what it means is this. What we are predicting is indeed the average value, or what we call expected value, of a dependent variable y for a given level or value of x. And symbolically, this is what we're actually predicting. So we're not predicting just like any just the value of y. It's actually the average value of y. Okay. I'll be able to clarify a lot of these through an example as we go through. So what do we mean by a regression line, regression equation? Of course, the regression line, therefore, is going to be the line of best fit for us, okay? And the regression equation is the equation of this line of best fit. Now, one thing about, before we see some examples, and by the way, again, I'm going to skip over all of the formulas. Remember, in this course, we don't care about doing things by hand. We want to do them using technology, in particular using statistical software. For us would be Minitab. Now, one thing about this this chart that you're looking at, okay, this graph. Don't worry about what these are, but if you're curious, these are the age of, I believe, the Orion automobiles. Orion age of some automobiles, and this is the price of those automobiles in hundreds of dollars. So for example, This number right here, 140 means $14,000. Okay, so that's what the y-axis is. Now, again, don't worry about this. What we want to talk about is, in fact, extrapolation. Extrapolation means going beyond the scope of your data. So we're looking at dangers of extrapolation here with the regression line. Okay, notice in here, let me get these lines off. Okay, so if you notice in here, for example, the highest value of x is 7. The lowest value is 2. And this is the lowest value of x. It is a 2. And the highest is 7. So any values of independent variable x that lies outside of 7 on the high side, means above 7, or anything that lies below 2, puts us in an extrapolation situation, which we are not allowed to extrapolate in regression. Okay, so this domain, in other words, of x here is going to be 2 to 7. So let's say for this particular example, if I have a regression equation, that regression equation is only good for values of x between 2 and 7. Which in this context means this model predicts the average price, selling price of an automobile, because that's what these numbers are. These prices are for automobiles. And again, the model is an Orion automobile. So we are allowed to predict in this domain, within these numbers. You're allowed to predict. So for example, I cannot use the regression model for this exercise to predict the price of a car that's a year old, or 0. 0 means brand new car, right? Which would be somewhere up here. But we're not allowed to do any of that. And by the same token, I'm not even allowed to actually do values that lie above 7. And here's why that could get me in trouble. Let's say I have an automobile, again, an Orion here. Orion, I believe these are the cars that this particular data set is looking at. So if I look at the price, let's say I have an Orion, it's 11 years old. That could happen. We could have 10, 11-year-old cars, right? So for a car that is 11 years old, the price is going to be about what, negative $2,000, $2,000 to $3,000. Well, this means you actually, if it's negative, price is negative $2,000, means you got to pay someone to get that car from you, which doesn't make sense. So just want to clarify what we mean by extrapolation. So remember, extrapolation is going outside of the domain. It's going beyond the domain of your independent variable. In this case, there you go. It's going here and in here. We are not allowed to do that. Okay, so just want to clarify these. Let's move on. Now, in the work that we do, okay, and again, this is the example for the Orions. That's exactly same data set, and there's actually 2 lines that are fit. These are the regression lines. Now, what we want to talk about here is actually, we're going to talk about the idea of influential observations. Okay, in particular, there's your influential observation. So what are influential observations? Influential observations are those observations that lie alongside, I have it right in here, they lie alongside the regression equation. So for example, let's say if I have a data point that is right down here, and then there's one down here, if naturally those were there, those would be influential. Influential observations lie away from the rest of the group, but it's very important that they lie alongside. So if you continue that line, see, alongside means this. Okay, so that's what influential observations are. Now, if these are influential, what exactly do they influence, right? Why are they called that? Well, it turns out that they influence the slope of the regression line. That's what influential observations do. So with this particular data set, you're going to see two separate fits. One is actually based on all data. Okay, based on all data. So there are no omissions, nothing. So this is the regression line. Okay, that's this one. Now, once you remove this one observation, once you remove that influential observation, look at the line now. See what happened? The slope of the line actually changed. So the inclination or the slope of a line actually changed. So influential observations actually influence the slope of the regression line. And what does that mean? Does that mean I remove it? What do I do with it? Well, just so you know, that's what they are. You got to be careful deleting data points, right? Because then we're going to make things work the way we want them to work. Okay. Now, for this one, I'm going to erase this part. We're going to talk about outliers here. Okay. And in fact, I don't need this because we know we're going to use the software, so I don't need to emphasize that. Okay. Now, we're talking about outliers now. So there is a marked difference between outliers and influential observations. Okay. So let me actually get my pen here. So what are outliers? So outliers, these are points that fall away from the regression line. Okay, so if you note in here, let's say, let me just add some more points. So I've got a whole bunch of points here. Okay, and I fit a line through these data points hypothetically. Now I've got a couple of points that are, you see that outliers fall in a vertical direction. These are away from the regression line. They're not alongside of it. A point that is alongside of it would be here. Let's see. That's alongside of it. That means it's an extension of that regression line. You see that? This would be alongside of it. All right. So outliers, they don't lie alongside. They lie in a vertical distance. Now, if you look at, for instance, I didn't want to do that. Sorry. Let me see if I can get it back. Yeah, I got it back. Okay. So if I actually, for these outliers, if I try to do this, let's say here, I'm at some level, x sub 2, and this is at x sub 1 for some level of x. I would expect at this point to get something in this range, right? Those are mostly what observed values of y are at that level of x. At this x1 level of x, these are mostly what they are. So you would expect to see y values in that range. Not something like this, and definitely not something like that. So that's what we call outliers. Now, what do you do with outliers depends on who the boss is and what you're allowed and not allowed to do. One thing we could do is we could de-emphasize the effect of outliers by making mathematical transformations, or if it's really clearly doesn't belong, you can simply remove them. Okay, so that's what we do with the outliers. Either remove them or de-emphasize their effect using mathematical transformations. We could do that. Now, here's an example. And again, don't worry about the formulas. We're just going to run this through Minitab and see how the regression comes out. So this example actually looks at some custom homes. These are in actual data in Phoenix, Arizona. Okay, so we have a random sample of 9. Here we have, there you go, we got, oops, sorry, didn't mean to do that. That's a highlight. There you go. So we have 9 custom homes. So that means n is 9. Okay. Currently listed for sale provided. So those homes provided the following information on size and price. So x is the size. That's your independent variable. See right here? X denotes the size in hundreds of square feet. Rounded to the nearest 100. And y is the price. So that's what this is. So those are clearly defined x and y variables. And y's are in thousands. Okay. So the numbers here are in thousands. And these are times 100 square feet. Okay. And what we want to do is we want to predict the price of 2,600 square feet home in that state. Now, notice here, by the way, 2,600. But if you look at the numbers, let's say this number, there's actually a home that's that size. 26. 26, remember, these are in 100 square feet. So 26 is what we actually have to put in our regression equation. So we don't, once we have it and we answer this portion, we're not going to put 2,600 in the regression prediction line. We're going to put 26. And one thing interesting though, we're about to predict the average price of a home that's 2,600 square feet in that estate. The actual number, the actual price is $540,000. Okay, so that's what that is. $540,000. So we're going to see what our regression model is going to predict. Remember this, 540,000, right? I'll try to remember that number. Okay, so we're going to continue on. Here, x is the size of a house. We're told that in the middle paragraph. And in that paragraph inside of that. And when I ran Minitab, and I'll show you in a moment, this is what the regression output looks like. So first of all, we have the price, right? There you go, right in here. That's our regression equation. Notice how descriptive it is in Minitab, which is pretty good, rather than using x1, x2, x3, y, and so on. So the price is 140. That's what this is. The price is 140 plus 15.89 times size. Remember, size is x. And that's the regression equation. That's all that is. So this is our prediction equation. Pretty simple, huh? So we can actually put in any number for size and get the corresponding price. Now keep in mind, remember we talked about extrapolation. So I'm going to go ahead and do something that Minitab doesn't do. I'm going to say the value of x here has to be between two numbers. The lowest number I can see is 22. Okay, so I'm going to go from 22, and the highest number I see is 40. So this is good for homes that are between 2,200 to 4,000 square feet. So if there is a house there that is about 5,000 square feet, this regression model is not appropriate for it, unless I can include a house that is 5,000 in my data. Then I'll be able to make that prediction. We also see the analysis of variance, or the Anova table, for this as well. So Anova is not just for the thing that we've done before. Every regression output actually puts out an Anova. The whole idea of Anova falls under what we call general linear models. So there is actually a connection between what we have done in earlier work with Anova for trying to test the hypothesis of equality of several means. You can also make it work for regression, where it has a different purpose in regression. You can use Anova to assess a relationship between variables also. Anyhow, so this is what the Anova looks like. So in this Anova, the source of variation. Remember, an analysis of variance is a partitioning of total variation in dependent variable. So here we have regression, and then we have error, the source of variation, and I'll explain these sources in a minute, how we go about actually why is it done this way. The degrees of freedom, don't worry about this one, but if you need to know, degrees of freedom is 1 because we are estimating 2 parameters, beta 0 and beta 1, the population slope, the population y-intercept. So it's number of betas minus 1. So because there are 2 parameters we are estimating, is 2 minus 1 makes it 1. We have 9 data points. So the total variation in y, that's the variance of y values, is going to be n minus 1, which is 8. So the error here, the difference between these two, is 7. I'll explain exactly what is regression and error using a chart in a moment. These are sum of the squares. These sum of the squares will lead to variations. Actually, they find the variances this way. Once you divide the sum of square by degrees of freedom, you get these numbers. Divide this number by 7, you get that one. The F ratio here is the ratio of 54,562 by 3,554. And of course the p-value here. What this p-value does, remember, anytime you see a p-value means somebody's testing a hypothesis. So what is this p-value actually testing? Okay, so what this hypothesis is that we are testing in this ANOVA, we have what we call a global hypothesis here. And the global hypothesis for the regression is that we do not have the right regression model. The null hypothesis says, in this case, what does it mean not having the right regression model? Remember, our regression model is a linear model here, a straight line fit. So what the null hypothesis says in this case is that the linear fit is not the right model for this. In other words, there is no linear relationship between x and the y. The alternative actually says the contradiction to that, right? The negation of that. So the alternative says that there is a linear relationship between x and the y. So this p-value is actually testing that hypothesis. Null says linear fit is not correct. Alternative says the linear fit is the right model. So we're going to reject the null and decide that yes, there is a linear relationship between x and the y. And there you go. Although it's not an impressive it's not an impressive linear relationship because not every point comes very close to the regression line. The red line, by the way, is the line of best fit here, the regression line. But then we have here some points like this one. We'll look at these in a few minutes. This one, and this one. We'll actually talk about those 4 points later. But all in all, this is the linear regression fit through the data points. And here to the side, we actually have some more information that Minitab has given us. We'll see these numbers later on. But let me hold off on what these are. But just to read them for you, that's R-SQ means R squared. And R-SQ ADJ, that's R squared adjusted. And these are percentages. And S here is 59.62. I will explain what this S is at the very end of this video. So, what is the predicted value of a house that's 2,600 square feet? Remember, that's what we want to find out. And remember, the regression equation is actually right up here, 140.1 plus 15.89 times size x. And there you go. So I just went ahead and put 26 in there, and if I did the math right, so our predicted value is about $553,000. Now remember, one of the values here, right in here, this was actually the actual price of a house that was listed at $540,000, and we are predicting on average a 2,600 square feet home is worth about 553,000. So it's actually higher than what it's supposed to be, right? And you can see it on our regression chart. There you go, right in here. This is 26. The prediction is slightly higher than that, as almost 55,000. So we are overshooting, overestimating the value. But then again, we are predicting the average price. That means if they have multiple homes that are 2,600 square feet, the average of those should sell on average for $553,000 roughly. I did around this, I dropped 3. Remember, these selling homes are in thousands. And note also, I did not put 2,600 here. You just put 26. Now, in all of our regression analysis, especially linear, we do translate, and not translate, but we do interpret, I should say. We do interpret the slope. The y-intercept, sometimes we interpret, sometimes we don't. It depends. If the scope of independent variable, right, the domain includes 0, remember x lies between two numbers, if one of those is 0, then we interpret the y-intercept, because that's when x is 0. But other than that, we do not usually interpret what the y-intercept is. But the slope we always interpret. And here I've gone actually through a chain of processes to where I get to the final answer. What does this slope mean in context? If you think of a slope as change in y over change in x, more specifically, y is the price, x is the size. So it's going to be the ratio of these two, price to size. And it's 15.89, right? That was the slope. Now, any number that the slope is, you always write it divided by 1. Always by 1. This way you have created a denominator. And that's 1 unit increase in x. You always take this to be positive. Okay? And remember, when x is 1, that means 100 square feet. 15.89 means 15,000. Let's say put 3 zeros. That would be, 15,890. That's what this is. That ratio is 158.9. And that's going to be actually, because at this point, this 15,890 is in dollars, right? So I can actually put the dollar sign there. And the number in the denominator is in just the square feet. It's no longer 100 square feet because I multiply 100 times 1. That's just a square feet, right? In fact, let me, while you're here, I'm going to copy and paste it there. So there you go. Now that's more descriptive, isn't it? So it's $15,890 per 100 square feet, which reduces down to price per square feet. See, that's meaningful information, isn't it? A lot of times you want to know what's the price per square feet. So let's say that's in Phoenix, Arizona, in San Diego, whatever that might be. Could be, I don't know, $300 per square feet, $400, $500, $600, depending on the location. Alrighty, now, here's another. This is not from Minitab, actually. This is from another software I used. So, same information. Here's the line of fit, and those are the same 9 points. 2, 4, 6, 7, 8, 9 points. Yeah. Now, if you look at these two, the ones that are in blue, remember, these are influential. Why? Because they're away from the rest of the group. If you remember, that's what we meant. And here's actually the cluster we're looking at. Not a big cluster, but nonetheless, it's a cluster. So these 2 points are clearly away from them, but they are alongside of them. You see that? They are alongside of them. So they are not outliers, but they are influential observations. Okay, and that's what they are. Now these other 2 points that I have, namely this one and this one, if you look at these again, the vertical distance from here to the line, is kind of excessive. And look at the distances of these two from the line. It's not that far away from it, right? So it seems as if we have two potential, I call them potential outliers, but there seems to be 2 of them. right, in here. So we have two potential outliers and a couple of influential observations in this data. And before we leave this and actually go take a look at Minitab, just a word of caution about linear regression. Again, remember, we're looking at or exploring a linear relationship in this segment between x and y. So if you have a data that clearly exhibits a bending, in this case, it could be exponential growth, it could be some kind of a bending, it could be a sine wave, whatever. Clearly a linear fit is a poor fit, right, for this data. So that's why you got to be careful that usually what happens is we draw the scatter diagram here, the scatter plot, and we fit whatever the visual suggests. So let's say if I knew how to fit a polynomial regression through this rather than just a line, that would do much better job of predicting, wouldn't it? I mean, this is what I mean. If I can somehow do this, look at that. You see that? Maybe there is a parabolic model that fits well, or it could be something of a higher order, higher degree. We don't know. But let's say if I knew how to do this polynomial regression, which by the way you can do in Minitab. So that's just the warning that we have here for you. Okay, so now before we actually get into linear correlation, let's go to Minitab and take a look at this. So I already have Minitab, but I need to readjust my viewing with the windows. So I'm just going to pause for a moment, and when I return, you're going to see a different screen here. Okay, everyone, so I'm back, and here it is. As I promised, I'm into a different screen now. So this is where Minitab is. I went ahead and typed in these sales, size and prices of the homes, and these are the 9 data points. This is what we mean by bivariate data. You have data on two variables, x is size, y is price. It happens that both of these are quantitative. And again, our assumption is that these sizes are fixed sizes, although they actually seem random to us, but we're going to make that assumption. I'll explain more about this later on, about this assumption. Okay, let's go run our regression. So we're going to go to stat, and you can actually go down. The second entry right there is regression. Notice regression is actually one of the most powerful tools in our disposal for predictions, by the way. And there are so many different kinds of regressions. The one that we actually look at is fitted line plot. There you go. This one modeled the relationship between one predictor, that's the x, and a continuous, right in here. Where did it go? There. And a continuous response using a linear, quadratic, or cubic regression. Now notice I mentioned that we can actually do regression for both quantitative and qualitative, right? But this description suggests, let me again, sorry I keep going, I just want to keep that verbiage here. Okay, notice it says predictor and a continuous response. Well, continuous suggests that y must be quantitative. However, we can actually do what's called here binary logistic regression. See that? And binary fitted line. It is possible to do these are all regression, by the way, everyone. See, regression is such a vast topic. For our work, for fitted line plot that we're going to do, actually it does require that y is quantitative. So let me remove these. The reason they're there is because I ran it earlier. Okay, so once you're in here, you click inside of this, you should see these two variables. So notice how Minitab calls them. Minitab goes by response and predictor. Remember, y is dependent, response, regressed, predicted, while X is called explanatory, predictor, regressor, and independent variable. So this is just what Minitab does. So where is your response? Well, response is price, right? So you just single click, select, or double click, and you don't have to. The first click, actually, when you double click, activates select, but since you do it so fast, you actually, this lights up and then this moves on. Okay, and doesn't light up, but it activates. And this is what I mean when I do a double click. Pay attention to select. What happens? I'm double clicking. You see what happened? It flickered for a moment. Anyways, so here are the type of regression models. So notice this is polynomial, linear, quadratic, cubic, first, second, third degree, because we're working with a first order model, so ours is linear. Now some of the options here you have, there you go, you can see this. Don't worry about these options, leave them alone. And the graphs here also, you have options on the graphs. Residual, a lot of these residual plots that you see here, these graphs test the assumptions of regression analysis. So don't worry about those, because again, as I mentioned, this idea of regression analysis, it's so vast, so deep, that we could spend months just on regression. So we're just going to give you just bare essentials in this course. Okay, hit OK, and there you go. Let me lower this data view, and so now you have more of the output view. And this is where I was getting those equations from. You see that? The equation, the model summary. You'll see this later on when I talk about the adequacy of model. And here's our analysis of variance, the Anova that we saw. I will explain where why are these sources of variability, where they come from in a minute. This was the graph that I displayed, and that's it. So you get all of these. And this is it. So this is all that you do with the Minitab for simple linear regression. Now I'm going to go back to my note and actually tell you more about now correlation. Okay, so now let's actually take on the topic of linear correlation here. So the question that rises is this: well, how strong of linear association is there between X and Y? Notice I've highlighted linear. Keep that in mind. Everything we're doing in this video has to do with the line of fit. So everything is linear. Okay, so in order to answer the question how strong of linear association there is, there are several measures of association. The one we're going to look at, it's called Pearson product moment correlation coefficient. Now some folks call it just a correlation coefficient and that's it. They leave out the words Pearson product moment. Well, Pearson is named after Professor Carl Pearson. And product moment here, product moment, that's actually a technical term. The moments of a function have a specific definition. So don't worry about this part, the person and the methodology, that's what these are. So simply correlation coefficient. So the answer to the question, we're going to use Pearson correlation to gauge or quantify the strength of association between X and Y. Now, if we do this for the population, which we never do, seldom if ever, the population correlation is rho, Greek letter rho, and the sample correlation is R. Okay, so that's what those are. Now there's again a formula that you're not going to see for R, because Minitab will give that to us. Now here I have several notes here. I have, I think, 3 notes here. First one, there are 2 types of correlation in our work. We have experimental and observational correlations. The observational correlation arise in observational studies, and experimental correlations arise from experimental studies again. So the difference between the two: if the correlation is observational, we cannot draw causation. And there you go. You may not draw causation in observational study. So for example, if the correlation between two variables is high, and these are observational correlations between two variables, I cannot say variable x is causing the values of y, variable y, to change. But in an experimental situation, I could do that. I can draw causation. So for example, let's say I'm baking 4 cakes, all of them for 20 minutes at 4 different temperatures. So I'm in a situation where my study is experimental, right? Because I'm not just picking a random temperature. Suppose my temperatures are 300, 350, 400, 450. Those are the 4 temperatures. See, they're fixed. And I'm going to bake these cakes. I could bake several. If I have 4 different ovens, which I should, I can bake, let's say, 2 pies at 350, 3 pies at 400, and so on. So in that case, I have an experimental correlation between temperature, and let's say my dependent variable is moisture content. Okay, I want to know how moist the cakes are. Okay, so I would assume that the higher the temperature, the more moisture will evaporate from the cake, so it's going to be less moist. In this case, I can draw the causation, and I can say that it is the temperature that's causing the moisture content to be lower at a higher temperature. Okay, so that's the idea of causation. I just want to clarify that. The second note I have here, this is very important again, that what this correlation coefficient is doing for us. It measures the degree of linear association. And it's simple linear, okay, not any other manner. So if you have a data that bends, quadratic, cubic, whatever, you're not going to use this. Although the software will output it, but we just skip it. We don't even interpret that. Okay, so that's very important also. And note 3 here is that, remember I said levels of x is fixed and y is random. So what if both x and y are random? Okay, well, if both x and y are random, then we have what we call the correlation model. And what this in effect means is that it really doesn't matter which variable you look at in relation to the other one. They're both on equal footings. So what that means further is that if you do a regression of y on x, x on y, it doesn't matter. Although you get, again, the fitted values will be different, but usually for this correlation models, we only are interested in correlations, not the regression. So there you go. Under correlation model, x and y vary together, and we assume each of their probability distribution follows a normal distribution, which their joint distribution, because you're looking at x and y combined together, not combined as in an addition, but simultaneously, I should say. Therefore, the joint probability distribution is going to be a bivariate normal. This becomes important when we do inferential methods in regression and correlation. Okay, so now we mentioned correlation Pearson correlation gauges or quantifies the strength of association between two variables, right? So here's actually where these values are. Mathematically, by the way, this correlation coefficient R lies between 1 and -1. So here I have a number line from -1 to 1, 0 at the center. And I made them symmetric. Okay, 0.4, 0.6, and so on. Now, and my 0.4 here, let me fix this. There you go. My decimal was too high up. There, that's better. Okay. So there you have that one. Now, okay. Sorry about that. Okay. Now this is a rough guideline. Okay. Now it goes from -1 to 1. These are the values of Pearson correlation. There's no way they can be less than that or higher than 1. Less than -1 or higher than 1. In -1, we have perfect, negative, inverse linear correlation. That's R at -1. Okay. Now, and so the correlation is very strong here. And then if you look as we get closer to 0, strong goes to moderate, then it becomes weak, poor to none. At 0, there is no linear correlation. So here's a case where the points are beginning to scatter about the line as we go from -1 to 0. But the slant is downward, right, for the line. And then as we work our way from poor to weak to moderate to strong, our values go in the positive direction. At 1, we have perfect positive correlation. And you'll see some diagrams in a moment. And there they are. So, this is what R1 means. You see that perfect fit? The line goes right through every single point without any error. And if that's actually true, then our model, regression model, becomes what we call a deterministic model at that point. A deterministic model has no error in it. So the example of deterministic models are right, for example, the area of a rectangle, length times width. In that case, if you do multiply length and you multiply by width, you get exactly the area. No error involved in that. Or, for example, F equal ma, force equal mass times acceleration, that's a deterministic model. E equal mc squared, that's deterministic. No error in that one. So, but linear fit means every point is on the line. That's perfect positive correlation. And then notice the correlation is getting smaller, smaller. Look at the spread of the points. See how they're beginning to kind of spread about the line and they're dissipating. And R is dropping. The negative correlation, R -1, is kind of like what's up here, except a mirror image, right? The difference between positive and negative is the orientation of the line. Here, as x increases, as x gets bigger, 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 so does y. It goes higher, 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 right? And this is what I mean. See, as x gets bigger, so does y. For inverse or negative relationship, notice as x gets larger, y actually drops. So that would be, for example, the price of an automobile or any kind of depreciation model that that assumes the value of whatever we're looking at drops over time. This one could be, for example, your salary, your income as a function of years you're at your current job. Usually, not, of course, if you leave the current situation out, but usually as the years go by, you get at least COLA, right? The cost of living adjustment. So typically, as you stay longer with your employer, your salary increases. So that would be the model, the regression model for income and years of experience. Okay. And then, of course, you have R is getting more and more negative here, and eventually it goes down to 0. Look at 0 here. There is no clear trend in this data. Okay, so you don't see any trend in the data in this case. And let's see. Next, we're going to go down to... okay, so here's... I'm just trying to clarify this, because this is so important, folks. A lot of times people just talk about correlations being this and that without knowing what exactly it is that they're correlating. So what I've done here is actually this. I actually have made up this data myself. So I created a data here, okay, that shows or exhibits a clear bending. You'll actually see the mathematical equation for this in a few minutes. So x goes from here to there, and these are the y values. Now, I went ahead and fitted a line through these. Look at that fitted line. It looks poor, doesn't it? Look at the correlation. It has a negative slope to it, negative slant, and it's at negative 0.21. That's on the poor side. So when the correlation, the point being this, when the correlation is near 0, it doesn't mean that there's not a relationship between x and y. It's just that the relationship is not linear. Now look at this one. Looks like there's a clear polynomial, in this case again a quadratic relationship between x and y, doesn't it? So if I know how to actually fit a quadratic equation or quadratic model through these data points, then my model is going to improve. So one thing, by the way, is like right in here, what I have down here, I'm looking at something right here. See this one? We're looking at that R squared. I'll explain about R squared in great details in a few minutes in this video. But for now, look at how small this number is. It's 0.04, right? So it's rather small. Keep that in mind. Okay, and of course, the line is a poor fit. And correlation is very poor. Now, what I have done here is, there you go, I fitted a curve through this data point. And when I did, notice I no longer, because R is now meaningless, right? The R is only meaningful, that correlation coefficient is meaningful if you have a linear relationship. So in this case, but R squared I maintain. Look at R squared up here, it's 0.04. Wow, look at the R squared here, 0.97. Now what is this R squared? We'll get to that in a few minutes, but this is a good thing. And the maximum this number can be is 1. It's at 0.97, means almost perfect fit. Notice it goes through 1, 2, 3, almost 4 out of 6 points. So that's pretty good. And this is the equation of that quadratic expression. Notice it's x squared. So this is not a first order regression model. This is a polynomial model. So negative 17.55. Okay, and that's not what you call it. That's that is when x is 0. Let's see, when x is 0, yeah, y would be negative 17. Okay, but anyhow, that's what these are. And I have a note here, the actual model that I created for this exercise where these points came out, this was the actual model, and look at Minitab, look how close it was able to get these numbers. 10.4, the actual number is 10, negative 17, there we go. Now in real life, you don't know this, right? We don't know this, but see, this just shows you that the stuff really works. This is a pretty good approximation to these actual numbers. what I did is I just created data based on this model, and I added some random normal error to it, and that's how I got these points. But anyhow, so we're done with the idea of correlation coefficient. Now let's talk about the R squared. So we're talking now, our topic is coefficient of determination. Now here I have a couple of questions. One, how reliable or effective is the regression model for making prediction? In other words, how good is this prediction model? Is it worth the trouble of making predictions with? And how accurate those predictions are? And that's what I have. A second one, how are we going to, well, that's what that is. Now the second question is actually like the logistics. How are we going to measure the effectiveness of a regression model? And this is where it's going to get a little technical. Okay, so what is a good regression model? Well, remember, for us, that means it's got to go through every point. That's the best case, right? And in fact, that is the inspiration for the work that you're about to see. So in here, in order to answer this, let's take a look at the answer to the question above is, we're going to look at the total variations in independent variable and see what percentage is explained or is due to the independent variable. So I guess what I need to clarify now is, what do we mean by explained variations? So as a measure of goodness, again, we're going to look at total variation in y, dependent variable, and we're gonna see what percentage of that total is explained by the presence of x. So for this work, actually I have two empty spots here, so let's actually proceed with this. Okay, so I'm gonna make up a point here. Okay, so this point, I'll call it y1, 15, and suppose, just making these numbers up, by the way, and oops, I didn't want to have a point here, sorry. I actually want to have, this is the predicted value, right, at this level of x, and here's your x, here's your y. Okay, now suppose the predicted value, that's y hat 1, is 11. Again, all these are made up. I know it's less than 15 because 15 sits above that. Now, hypothetically, let's say, because I singled out just one point, one data point here, this one, right? Now, let's say the average for all y values is 10. Okay, now, if I look at, and let's say here now, also, this time, here is this point, and this is the predicted. Again, I'm going to go y1 equal 15 this time. Y hat 1 equals to, looks to be about, I don't know, 13. There, because it's actually closer, right? That point is actually closer to the 15. So I'm going to go 13 on this. And I still have that same y bar equal 10. Okay, now, if you look at the regression line in the bottom, just for this one observation, it looks like this is a better line of fit, isn't it, than this one, because my predicted value here is farther away from 15 than this one is. This is closer, so this is a better line of fit. Okay, now let me actually pursue this further. I'm going to extend this line here, extend this one, and of course this is x bar, or I'm sorry, this is y bar. Okay, now if I look at the distance from the observed value to the average, So I'm looking at y1 minus y bar. And that's going to be what? 15 minus 10, that's going to be 5, right? Now the distance of 5 is actually partitioned into two parts, right? This distance, which is 15 minus 11, and that's going to be y1 minus y hat 1, and that's 4 units. And this other part is 1 unit, right? And what is this one? This is y hat 1 minus y bar, and that's only 1 unit. So you can actually see that if I add 1 and 4, I get 5, the total deviation of observed value from the mean of dependent variable y. Okay. Now, if I look at the ratio of, in this case, y hat 1 minus y bar. That's this distance right in here. Okay, that's this distance right here. There. That's that distance. Okay, from here to here. That distance is 1 unit. If I divide y hat 1 minus y bar divided by the total of y1 minus y bar, which is the total of 5 units of deviation of observed from the average. Okay, if I do that, then what's going to happen is I'm going to get a number here, right? Which is simple, 1/5. That's 0.2. Remember, the one model I have, regression model here, is not as good of a fit as this one is. So if I take the ratio again of the distance from predicted value to the average divided by the total deviation from observed to the average, that's 0.2. Now for this one, the second scatter plot or scatter diagram, which is a better regression fit for that observation, if I do the same thing, and there you go. So the total deviation is still 5, isn't it? Right, that's not changing. What's changing is how close I'm getting to it from the regression line. So this time this distance is 2, and the distance below it, 13 minus 10, is 3. Okay, so if I look at the ratio of this distance, that is y hat 1 minus y bar, divided by y1 minus y bar, this time that distance is going to be what? 3 divided by 5, or 0.6. Look at this number, look at that number. The higher number is a better number. Better in the sense that, look at the regression line. The line is closer to the actual value. Okay, so this is a better fit. So this is going to be the basis for our adequacy of model. How are we going to decide whether the regression model is a good line of fit? And that's what the answer is. So let's look at total variation and see what percentage of variation is explained or is due to the presence of X. So what happens is that these numbers, they turn them into 0.6 means 60%. 60% of 5 is 3. So 60% of that variation of 5 units is due to the regression. Okay, now our terminology here, regression terminology, there. y1 minus y hat 1 is called explained variation. And what is y1 minus y hat 1? y1 minus y hat 1 is this right in here, this part. That's y1 minus y hat 1. Y hat 1 minus y bar is this other part. Okay, so that's this one. Okay, so the one on top, the one above in highlight yellow, this is explained, and the one below it is unexplained. Okay, and from that we actually come up with what we call coefficient of determination. Now let me show you this drawing now that kind of brings it home based on what I just used my numerical example on. So for this one now, what we're looking at is decomposition of the deviation of observed from the mean. Okay, observed value from its mean. So this is the observed value, and here's the mean, and that's the mean right in here. So if you look at this distance, see, that's the deviation of observed value from the mean. Now, that deviation is going to be partitioned into two parts. Okay, so it's going to be made up of this part and this other part. This part, deviation explained by the regression. Oh, make sure I go up here. Sorry, I got these switched out. There you go. It's the other way around. So they call this portion explained. Maybe I should just to clarify. There you go. So I'm not confusing you here. Okay, so this is going to be explained, and this is unexplained. Okay, that's why I had 1 minus y bar. So this is what is explained by regression, because this part, again, this distance changes whether the line goes here, here. So that's why it depends on where the line falls under that observation. Okay, so there you go. And then this other part of it is going to be unexplained. This is the part that is not explained by the regression. Okay, and that is why in the Anova we had the regression and the error. Okay, so this is again the regression, and this part is what the error is in our Anova. Okay, and let's see, let's go further. So these deviations become squared, and they're called square deviations. And because we look at these deviations for the entire data set, not just one observation, so we add them up. Okay, when we add them up, then we have their sums, and they square them, because if they don't, again, they just add to 0. So it's the sum of the squares. Now, there are 3 sum of squares in regression. These 3 sum of squares are the total sum of squared, this one, and then you have a regression sum of squared, and you have what we call the error. The regression sum of squared, this is actually the explained portion, and the error or residual is the unexplained portion. Okay, that's what those are. And these are symbolically what they are. They're exactly what I had earlier, and you can find them right up here. See, again, I have them in here. Okay, and this is the regression identity, that the total sum of a squared is actually broken down as sum of squared regression plus error. That's why in your Anova you have the row that's regression, and then you have error, and then you have total, remember, and this was source, something like that. It's because of this identity. Okay, now let me remove all of these, and we're clean now. Okay, so based on that regression identity, I went ahead and wrote down in sigma notation what that identity is in sigma notation, and just for the record, And this is what that coefficient of determination now is defined. So this is the ratio that I had with my example. In one case it was 1/5, and then latter case it was 3/5, which was a better fit. So for this one, the coefficient of determination is the percentage, like, right, the word proportion here means percentage. It's the percentage of variation in the observed value of response that is explained by the regression. This explained by the regression, you can think of it as due to presence of independent variable. Now, the best that could happen is when SSR, when the line, when you have a perfect fit, you'll see that in a minute. When you actually have a perfect fit, SSR and SST become equal. So this ratio R squared is going to be between 0 and 1. 1 is the best that could happen. This is what happens at 1. You see that? The observed values are the actual solid dots. The predicted values are in squares. Okay, notice they coincide. They're identical. So here's a case where y minus y bar will be exactly equal to y hat minus y bar. And the reason for that is because these are the same. The observed, this is the observed value, and this is the predicted value. When these are equal, then the left and the right side will be identical. Okay. So there you have that. So when it comes to R squared, we would like to have high and large R squared. Now this coefficient of determination, by the way, we're going to use it in simple linear regression, but it actually works in multiple regression also. Remember, the R, the Pearson correlation coefficient, only works for linear, but R squared works for nonlinear, any kind of regression. And in case you wonder, well, is there a relationship between this R squared and the R that we just did? The answer is yes. If you indeed take the square root of R squared, you get the correlation coefficient. And if you square R, if you take R and square it, then it becomes coefficient of determination. So that's how they are related. Now, let me also emphasize, what do we mean by coefficients here? Coefficient. It's up here. Typically in all fields of science, especially in mathematics also, and in particular statistics, anything that's a coefficient, this number that we call a coefficient, that means it does not have any units attached to it. So let's say you have the correlation coefficient between x and y is, I don't know, 0.7. Is that $0.7? Is that 0.7 square feet? What is it? Well, there is no units attached to it. It's just an index, like, I don't know, like the Dow Jones Industrial Average. And if Dow Jones is at 25,000, it doesn't mean it's $25,000. It's just an index. Okay, so that's what both of these numbers are. The coefficient of determination is just a number, and the correlation coefficient is also just a number. Now, the coefficient of determination is a percent. Okay, it's a proportion. So this is actually a percent. Whereas correlation coefficient is not a percent. It's just a decimal, although they are related together in this manner. So again, coefficient of determination will be a percent. And what percent exactly is it of? It's right in here. It's the percentage of all of that. That is what R squared is. Okay, and I think we are good in this with this. And oh, by the way, let's say if I have R squared, this is important. Let's say if my R squared is, I don't know, 81. Okay, and I want to find R. I take the square root of it, right? When I take a square root, I get plus minus square root of 0.81, which is plus minus 0.9. So how do I know? Do I choose plus or minus? It turns out that the sign on the correlation coefficient, as you can see, could be positive or negative, right? R squared, by the way, is always positive because you're squaring things. Okay? But correlation could be positive or negative. So which one do I pick? Positive 9 or negative 9? Well, it depends on the slope. The sign on R is exactly the same as the sign on the slope. So if slope is positive, you choose positive 0.9. If slope is negative, you choose negative 0.9. So again, it's the slope of the regression line which determines whether the correlation is positive or negative. Okay, let's continue on. And here again I have explain variations. What do we mean by that? Explain variations show how much of deviation from the mean is reduced when regression line is fitted to the data points. Now, for our housing prices, the example we did earlier, this is what we have, the model summary. This was part of the output in Minitab. So here's R squared. You see that? 0.6868. Now next to that we have R squared adjusted. In other words, we have adjusted R squared. The adjusted is 6421. Okay, so it's 64%. Well, what is the difference between them? In first order regression model means one independent variable. We ignore that. Okay, because we only have one variable. But in multiple regression, we actually keep track of this. The word ADJ here means adjusted. Okay, well, what are we adjusting for? This R squared keeps track of how many independent variables are in your model. And with multiple regression, we could have multiple values or multiple variables, independent variables. So that's why that comes in handy. If we have too many independent variables, then we will actually get penalized for it, and this number will be much different, typically lower, much different than this number. So for what we're doing right now, do not worry about do not worry about R squared adjusted, because we're not working with that. So ignore that. Okay, just focus on R squared. What is this S? I'll explain that in the end. Okay, and that's the last thing we do, is tell you what that is. Okay, so let's continue on. What does that, remember we were talking about the coefficient of determination, R squared. So what is the interpretation of this? Here's the interpretation. Remember, R squared is a percentage. R is not. 68, almost call it 70%. 70% of total variation in home prices, that's in Y, right? Dependent variable that are explained by X, the size. So in other words, 70% of the reason why the homes are different in that location. Why are their prices so different? Well, 70% of the reason is the size of the house. That means 1 minus that will be about 30%, right? About 31, 1.5. Excuse me. About 31% of the reason for why those home prices are different, we don't know. There are other factors affecting the price of those homes. Almost 70% is the size. Now, what are the other 30%? I don't know. Could be the number of car garages, number of bedrooms, bathrooms, so on and so forth, the amenities. And that's what gets us into the topic of multiple regression. Now, just want to show you where that 0.6868 has come from. Okay. So, R squared is SSR over SST, and these numbers I grabbed them from the Anova table. Okay. And you divide it, you get 0.6868. So that's how that's done. Now, we're almost done with this, folks. We are now actually looking at, there are 4 assumptions associated with a linear regression model. So these are the model assumptions. 1, linearity. Remember, we assume that linear relationship makes sense. And then the second assumption is homoscedasticity. Some call it homogeneity of errors. Okay, so what that says, or what that means, is that the variance of residuals, remember the difference between observed and predicted, the residuals is the same for any value of x around the line. I will actually show you an example of that in a moment where the case is not true. Assumption 3, of course, we always have assumption of independence, that observations are independent of each other. And of course, the normality. This one I actually will do an illustration for you of this one also. That one. Normality. For any fixed value of x, y is normally distributed. And that's pretty cool assumption and pretty cool graph to see. So, this is number 2 violation. The homoscedasticity. If you look at this fanning effect. You see the fanning? What happens is the variations increasing, right? As x increases. So this shows us that the assumption of homoscedasticity is violated. And indeed, if it's not homoscedastic, then it's got to be heteroscedastic. So this shows heteroscedasticity. And that's what that assumption means. So what do we do with this data, right? Well, there are actually mathematical transformations we can do. And Professor Tukey, remember we talked about multiple comparisons using Tukey method and Tukey-Kramer methods. Well, Professor Tukey actually has come up with some transformations which help reduce the variability in the data sets. So that's what the remedial action is here. Use mathematical transformation to try to kind of linearize these so they're not so variable. Okay, maybe take natural log of them or take the square root of them and what have you. Now, this fourth one, this one is the one I'm about to show you. Okay, what do we mean by for any fixed value of x, y is normally distributed? This is what that means right in here. So, notice here I have x and y. I have x and y. X is independent, y is dependent. So I have a regression line drawn. Okay, so this is a regression line. Okay, now these are fixed values of x, x1, x2, x3, 3 levels of x. So this could be, again, for instance, a home that's 2,000 square feet, 2,500, 3,000 square feet. The price of the home is actually allowed to vary. Now, according to regression line, there you go, the bigger the size, the greater the price. So hypothetical, this is the fitted regression line. Okay, now, what we're assuming is that the distribution of y values, these are prices of homes of the same size in that same locale. The distribution is normal, and the center of that normal distribution is given by the regression line. You see that? That's why when we predict, I mentioned we predict the average price of a house of that size. So in general, you're predicting the average value of dependent variable for a fixed level of x. Look at for the second level of x. You're looking at, again, the center of this distribution is given by the regression line. And the deviation is the same. See, sigma, sigma, sigma. Same deviation at every level. And finally, for the third level, the center is given by the regression. So I guess it's safe to say that here the y hat. So what is y hat that we are actually finding? Y hat is the expected value of random variable y for a given level of x. That's what y hat is. Okay, hopefully you can follow that now. And that was our second assumption. I'm sorry, the fourth assumption, the normality. Now, the very last thing that we talk about here is this. Remember I told you, I tell you what that S is. In fact, this S is a point estimate of sigma. That's what that is. Okay. So, there you go. You see that sigma? This is what S is. S is a sample estimate of that. And it's the same number for every level. That means any prediction we make, and for this model, for price of any size home in that location, without extrapolation, our estimates could be off by as much as almost $60,000. So that's rather high, isn't it? Now the reason it's so high, 60,000, part of it is because our R squared is not as impressive as it should be. With R squared, the higher the better. Now, as far as the adequacy of the model, remember the whole discussion where this discussion of R squared came about was, how do we gauge the adequacy or the efficiency, the effectiveness of the model? How good is this model? So, we're done with it. Yeah, so okay, so let me actually put some closing remarks here for you. If you look at R squared, so for example, this would be R squared from 0 to 100%. Okay, so and this is 50% mark. So usually we would like to have 70% or more for R squared values. And if that is the case, at 70% we call the model adequate for prediction. At 100% the model becomes deterministic. Remember, no error. That's a pie in the sky. That's the best that could happen to us. So we would like large R squared, so 80%, 90%, and higher. Those are the kind of R squares. The bigger means, the larger means the better the predictive power of the regression line is. Okay. So there you go. With that, we are done with this topic. Rather lengthy topic too, almost 2 hours. So I'm sure you had to pause it several times throughout the lecture, right? Anyhow, sorry I'm scrolling fast, I know. Just want to make sure I covered everything. Yeah, looks good. Okay, so we are done with this lecture. And the only thing remaining is multiple regression, which is an extension of this one. So we'll actually look at multiple regression example, and we'll run that in Minitab also, and that will be the last thing we do for this segment of the course. So with that, we are done with this lecture, and we are done with the subject of regression and correlation.